So we are starting with the topic B5, current and circuit. In this topic, we will be starting with the basic concepts of electricity and current. After that, we'll see what is potential difference, what is resistance, what is resistivity, series and parallel circuits, and the internal resistance of a battery that we are going to discuss in this topic. So say there is a battery connected here. Instead of understanding this way, let me consider one person. I can name this person as Mr. Coulomb. Mr. Coulomb is carrying, say, 120 joules of energy, and I can also say 120 joules per coulomb this person is carrying energy. And now, like an electron, this person is moving from here and reaching this resistance R. Suppose the person is here carrying 120 joules of energy per coulomb. One resistance is here. This resistance will be allowing the Mr. Coulomb to pass through it, provided it gives some energy or provides some energy to the resistor. Say it has given some 15 joules of energy. If 15 joules of energy is given, here the energy left out will be 105 joules per coulomb. Similarly, this resistance will also oppose the flow of current, or will have to supply some energy to this resistance so that Mr. Coulomb can pass through it. So here say energy is 105 joules per coulomb, and this resistor required something 30 joules of energy. So the energy left out here would be 75 joules per coulomb, and the entire 75 joules of energy will be supplied to this 50 ohm. So energy left out is 0 joules per coulomb. Okay, so here you can see the energy spent by Mr. Coulomb here is something like 15 joules per coulomb. Or if I connect a device called voltmeter, I'm going to show it this voltmeter measures the potential difference. Now how this voltmeter works, this voltmeter acts like a calculator that only measures the difference between two energies. So this potential difference here would be something like 15 joules per coulomb. But as this device has been the device is discovered by Mr. Volt, so instead of joules per coulomb, we can write 15 volt here. Similarly, I can connect another one voltmeter here, or we can say in layman language another one calculator here, which can calculate the potential difference between these 2 points. That would measure something like 30 joules per coulomb, or I can say 30 volt. Now 75 joules per coulomb is the energy left after 20 ohm. Now Mr. Coulomb is passing through this, spending the remaining energy. So if I connect another one voltmeter, that would measure 75 joules per coulomb here, or that is 75 volt. Okay. Now if I connect another voltmeter here, this voltmeter would measure the total energy spent by Mr. Coulomb. That would be around 120 joules per coulomb. Now in physics language, this is called the EMF of the battery, electromotive force of the battery, or total energy spent by Mr. Coulomb in circulating or in moving from one point to the another point of the circuit. Now here, if I add it up, all this potential difference, I shall be getting the EMF. Here you see EMF is 120 volt, and that is 30 plus 15 plus 75, that gives you 120 volt. So we say in a series circuit, the potential difference or the voltage get added up. Now I can show you by actually adding a voltmeter whether this concept is right or wrong. Let me connect voltmeter across this. As I said, this voltmeter acts like a calculator. Here Mr. Coulomb has spent some 120 volt, or we can say 120 joules per coulomb. Same voltmeter I had taken here, okay, in my explanation. If I keep it here, look, the energy spent by the charge is 15 volt, right? Similarly, if this terminals, if I connect across 20 ohm, that gives you 30 volt or 30 joules per coulomb. Similarly, voltage across this 50 ohm can be calculated, which is 75 volt, right? So this voltmeter acts like a calculator. In physics, we have number of things we write in a shortcut way. Which are the number of things? Like sometime we learn in mechanics that joules per second is basically watt. Similarly, we say Newton per meter square is Pascal, name of a scientist. So here, joules per coulomb can also be written as something called volt, V. Okay, so voltage nothing but the energy per unit charge, the way I have drawn Mr. Coulomb. So we said joules per coulomb. That means Mr. Coulomb is carrying that much energy. In actual electricity or in actual wires, electrons actually move by carrying energy. But now again there is a confusion here, that what moves? Is it electron or the positive charges? But actually electron moves. But in our IBDP, we always say that current flows from positive terminal to negative terminal. Here you can see the electrons are moving from negative terminal to positive terminal. But when you deal with conventional current, the conventional current is always opposite to this. Conventional current is from positive terminal to the negative terminal. So here we understand what is electronic current and what is conventional current, but formula will be the same. Now in IGCC we have learned that this resistance is basically potential difference upon the current here. Now you can talk about this resistance here. Let me apply here. Resistance is 10 here, okay, and what is the potential difference across this? 15 divided by the current here, and that current here is 15 divided by 10, that gives us 1.5 ampere, and that current remains same everywhere, because you need to understand in terms of electron. If one electron is getting pushed, only then the other electron will move. Okay, that's why current in the entire circuit remains same. Resistivity denoted by rho here. So we know resistance R is proportional to length of the conductor. Resistance R is inversely proportional to area of cross section. Here look, if I consider a resistor like this, here the length of the resistor is L and area of cross section here is basically A. But in IB, sometimes they ask you questions in terms of volume. So that concept is not included in many textbooks. So what we can do here, R we know is equal to a constant rho L upon A. This resistance can be written in terms of volume. How? I can multiply the numerator by L and denominator by L like this, so that this gives you rho L square upon the volume. V is the volume here. So the resistance is written in terms of volume. If we are stretching or extending this resistance to a new length, the volume remains constant. If volume remains constant, then we say R is proportional to the length square. Okay, when the volume V is constant. This is basically resistivity, and remember The resistivity doesn't depend on physical properties like length and volume, but resistivity depends on the chemical property of the material. Now, in this topic, just I'm summarizing, these are the two important concepts, but I'm just summarizing it that what exactly we are supposed to know in this topic. First is the electric current I equal to Q upon T. That is the first things you are supposed to know. Second thing you are supposed to know is the potential difference, which is electrical energy over charge. That is your potential difference. Next, the Ohm's law. Ohm's law says that I is proportional to V, or we can say R equal to V upon I. Next equation, R equal to rho L upon area, or we can say rho L square upon volume. The next formula is on energy. So this electrical energy is given by voltage into charge equal to VIT equal to V square upon R into T equal to I square R into T. Next comes electrical power. Power is energy upon time, or I can cancel time from this. So VI equal to V square upon R equal to I square R. That is electrical power. And the last one I should write the EMF. The EMF equal to I into small r plus capital R, where small r is called the internal resistance of the battery. This is the whole summary of B5. So first I explain what is resistivity, what is voltage, what is current, and the list of this formula. That is more than enough to get everything in this topic. So here we are winding up the class on current and circuits.